It's a beautiful day in this neighborhood, a beautiful day for a neighbor. Would you be mine? Could you be mine? It's a neighborly day in this beauty wood, a neighborly day for a beauty. Would you be mine? Could you be mine? I have always wanted to have a neighbor just like you. I've always wanted to live in a neighborhood with you. So let's make the most of this beautiful day. Since we're together, might as well say, would you be mine? Could you be mine? Won't you be my neighbor? Won't you please? Won't you please? Please won't you be my neighbor?
Good morning, everybody. Welcome to Tibbetts Physics. What is crappinin'? Today we are going to look at practice problems from Chapter 5, which is on work, energy, and power. Question number 1. Given the situation below where a spring has a 10 kilogram mass hanging on it, which is position A, then a 20 kilogram mass is placed on it, position B. What is the spring constant of the spring? If you look at the picture, we have a spring without a mass that's in its rest position. We add a mass to it, causes the spring to stretch. And then we add 20 kilograms and it stretches even more. And what we want to find is the spring constant. We're going to start off this problem with Newton's second law. A equals the net force all over the mass. In this case, we have two forces acting on the spring, or on the object, I should say, sorry. Going down is the force due to gravity, F sub g, and going up is the spring force, F sub s. So let's plug that in for F net. A equals F sub s minus F sub g all over the mass. Let's next multiply both sides by the mass. That brings us to MA equals F sub s minus F sub g. In this case, we can assume that the mass is just hanging here, so its acceleration is 0, which means MA goes away. We can add FG to the other side. That leaves us with F sub s equals F sub g. Our goal is to calculate the spring constants. So we have to break down the spring force formula. That's K times X. We're given the mass of the object, so we have to calculate its weight, which is M times G. We're solving for K, the spring constant, so we'll divide both sides by X. K equals M times G all over X. I'm going to use the 10 kilogram mass to analyze this situation. So K equals 10 kilograms times 9.81 meters per second squared all over the spring stretch. It starts out at 5 meters. And I know this picture is bad, but let's say it's stretched down to 50 meters. So its total stretch is the final position minus the initial position, or 50 minus 5. Plug and chug, and we get the spring constant to equal 2.18 newtons per meter. Letter B, what is the spring's potential energy at position A? The formula for elastic potential energy, PE sub S, equals 1/2 kx squared. We know what K is now. We know what X is at position A. So now we just want to solve for PE sub S. 1/2 times 2.18 newtons per meter. And X is, it's stretched down a total of 45 meters. That's 50 minus 5 meters. And we have to square that number. Plug and chug, and we get an elastic potential energy, PE sub S, to equal 2,207.3 joules. Letter C, what's the elastic potential energy at position B? Same formula, PE sub S, 1/2 kx squared. The spring constant stays the same, that's how strong the spring is, 2.18 newtons per meter, times, it started off at 5 meters, stretched down to 95 meters, so its total stretch was 90 meters. Quantity squared. Plug and chug, and we get 8,829 joules. Oops. 8,829 joules, sorry, of elastic potential energy. Number 2, Mike is dragged 10 meters across a frictionless surface by a rope that makes an angle of 30 degrees with the ground. The tension in the rope is 800 newtons. Letter A, draw a diagram. So we have Mike. He's our object, that's the dot. He's being dragged across the floor with a force of 800 newtons. Let's just call that F pull. And it makes an angle of 30 degrees relative to the ground. Theta equals 30 degrees. We could find the component forces. F sub x, that's the horizontal force pulling on Mike. And F sub y, that's the vertical force pulling up on Mike. And in this case, he's dragged towards the right. Let's call that D sub x. And that equals 10 meters. Letter B asks us, what are the horizontal and vertical components of the applied force? All we want to do is find F sub x and F sub y. F sub x is F, in this case F pull, times the cosine of theta. F sub x is 800 newtons, times the cosine of 30 degrees. F sub x equals 692 newtons. The vertical force, F sub y, is F pull, or just F, times the sine theta. Same thing, 800 newtons times the sine of 30 degrees. Plug and chug, and we get a force in the vertical direction equal 400 newtons. Letter C, how much work is done in moving Mike across the floor? Since Mike is moving to the right, the force that's doing work on Mike is the horizontal force, because he's moving just in the horizontal direction. So the work done on Mike, we could say, is the work in the x direction. That's the force of Mike in the x direction, times his horizontal distance. That's 692 newtons times 10 meters, which means 6,920 joules of work were done on Mike to pull him across the floor. Next problem. A 5 kilogram object is moving 5 meters per second on a frictionless horizontal surface. How much work does Talon do when she exerts a force on the object to speed the object up to 10 meters per second? So let's write down our knowns in this case. The mass is 5 kilograms. The object is initially moving at 5 meters per second. It speeds up to 10 meters per second. And we want to find the work that Talon does to speed the object up. Well, we know that work is equal to the change in energy in this case, the change in energy, because it's on horizontal surface and moving, is just the change in kinetic energy, which means it's the final kinetic energy minus the initial kinetic energy. The formula for kinetic energy is 1/2 mvf squared in this case, minus 1/2 mvi squared. And to find the amount of work, now it's plug and chug. 1/2 5 kilograms times 10 meters per second squared minus 1/2, mass is still 5 kilograms, times 5 meters per second squared. Plug and chug, and we get the amount of work that Talon does to equal 187.5 joules. All right, number 4. Now we're looking at a conservation of energy problem. A 10 kilogram rock is dropped from a height of 20 meters. What is its velocity just before it hits the ground? There's two ways of analyzing this. We can either use constant acceleration or projectile motion. But for this lesson, we're going to use conservation of energy. To do that, we're going to set up an LOL diagram, similar to our if charts, where we have what are the energies before the objects, or the object's initial energies, and what are the object's energies afterwards, so when something changes. In this case, the object's possible energies for this scenario are potential energy, would be gravitational, kinetic energy, and work. Afterwards, the possibilities are still gravitational potential energy, kinetic energy, and we'll add Q here, which is internal energy. Looking at letter A, what is the velocity just before it hits the ground? So initially, it's 10 meters above the ground. That's gravitational potential energy. The object is not moving, so there's no kinetic energy. And there's no outside force or outside factor other than gravity. I'm pulling it down. Afterwards, it's right above the ground, so PE sub G is 0. And all that energy was transferred to kinetic energy. And for letter A, there's no internal energy. Which means to write our formula, we're left with PE sub G before is equal to just kinetic energy afterwards, so KE. Guess we should put a before and an after, just in case we have more energies. The goal is to solve for the velocity of the object. That's from the kinetic energy formula, 1/2 mv squared. We don't know the gravitational potential energy, but we can calculate it. That's mgh. We're solving for the velocity afterwards. Let's multiply both sides by 2 and divide by the mass. As we could see, when we divide by the mass, they cancel out. So let's multiply both sides by 2, then square root it to get the square. That leaves us with v is equal to the square root of 2gh. Plug and chug. 2 times 9.81 meters per second squared times a height of 20 meters gives us a velocity of 19.8 meters per second. Technically, because it's going down, and when we take the square root, we can take the positive or the negative. So we can take the negative value of that square root. Letter B. What is its velocity just before it hits the ground if 200 joules of energy is transferred to internal energy due to air resistance? So now our chart for before stays the same, just has gravitational potential energy. But afterwards, It still doesn't have gravitational potential energy because it's just above the ground, or as close to it as possible. But some of that energy was also converted to internal energy. So we have to include Q. Our new formula will be, for this scenario, gravitational potential energy before equals kinetic energy after plus Q, internal energy. Let's break down both of the formulas. mgh equals 1/2 mv squared plus Q. We're solving for V, but this time we have to subtract Q first. mgh minus Q. And then we can multiply both sides by 2. Divide both sides by the mass. Square root it to get rid of the square. And that gives us the velocity. V equals 2 times the mass, 10 kilograms, sorry. That's a parentheses. Times 9.81 meters per second squared. Times 20 meters. Minus Q, which is 200 joules. Close our brackets. All of that is multiplied by 2. Divided by the mass of 10 kilograms. Plug and chug, and we get a velocity of 18.8 meters per second. And again, let's make it negative since it's going down. As we can see, the velocity slowed down by about 1 meter per second when we included air resistance. Oops. Number 5. A 54 kilogram ice skater, Zach, moving at 3.2 meters per second, collides with a 44.7 kilogram Mariah skater who is motionless. They then slide together along the frictionless ice. What is their velocity after the collision? They're colliding, which tells me that this is going to be a conservation of momentum problem, at least to start off with. So let's make an if chart. If you want, you can do an MVP chart. Initially, we'll call Zach M1. He has mass, and he's moving to the right, V1. Mariah has mass, M2, and she is not moving, which means she doesn't have momentum. We can write for our first part of the formula, M1, V1 initial equals, afterwards they collide together, so their masses are combined. And for now, we can assume that they're moving to the right. The momentum after would be M1 plus M2 times, let's say, V sub F. And we're solving for V sub F. Let's divide both sides by M1 plus M2. VF equals M1 V1I all over M1 plus M2. V sub F equals 54 kilograms times 3.2 meters per second all over the sum of the masses, 54 kilograms plus 44.7 kilograms. Plug and chug, and we get a final velocity of 1.8 meters per second of Zach and Mariah combined. Letter B, how much kinetic energy was lost in the collision? So let's look at the initial kinetic energies of the system before and the final kinetic energies of the system after. To figure out how much was lost, we'll subtract those. So letter B, sorry, I'm running out of space. Initial kinetic energy. As we could see in this scenario, the only object that is moving is Zach, so he's the only thing that has kinetic energy. So 1/2 mv1I squared. initial kinetic energy, 1/2, 54 kilograms, times 3.2 meters per second squared. And we get Ke sub I to equal 160 joules. To find the change, again, we want to find the final kinetic energy as well, so Ke sub final. That's of the entire system. In this case, it's Zach and Mariah combined, as well as their combined velocities. 1/2 m1 plus m2 times Vf squared. Ke sub F equals 1/2, 54 kilograms, plus 44.7 kilograms, times, 1.8 meters per second quantity squared. Plug in chug and we get a final kinetic energy to equal, 160 joules. The initial kinetic energy, I had a typo there. The initial kinetic energy is 276 joules. Sorry about that. So if we want to find the change in kinetic energy, or how much what was lost, we do Ke final minus Ke initial. That's 160 joules minus 276 joules. And we get negative 116 joules of energy was lost. Now by lost, we mean this energy, it doesn't disappear, but is transferred into another form that was kinetic energy. Letter C. What fraction or percent of the kinetic energy was lost? So 116 joules of kinetic energy was lost out of a potential, or a total of 276 joules. We'll multiply by 100 to get the percentage, and that gives us 42% of kinetic energy was lost. Or again, transferred into a different form. Alright, 2 more problems to go. Number 6. A skier, Logan, of mass 70 kilograms, is pulled up a slope by a motor-driven cable. How much work is required to pull Logan 60 meters along the 30-degree slope, assuming it's frictionless, at a constant speed of 2 meters per second? We're on an inclined plane, so let's draw a free body diagram of forces on an incline. I'll draw the incline itself. Logan will be a dot. The forces acting on Logan are straight down, we have F sub G. Perpendicular to the surface is the normal force F sub N. And we have a force pulling Logan along the incline. Due to the motor, let's call it F sub P. We could break down the components of the force due to gravity in its vertical direction. So this purple line will be FGY. And the force of gravity in the horizontal direction, parallel to the incline, FGX. We can make those solid lines. So I only do blue for FGX. Also, the angle theta is 30 degrees relative to the ground. The angle between FG and FGY is also 30 degrees. If we look at our coordinate plane, the y-axis is along Fn and FGY, and the x-axis is along FGX and FPull. We want to find the work being done to pull Logan. that's the force pull, that's in the x direction. Let's analyze Newton's second law in the x direction. A equals F net over the mass. The forces acting on Logan are the force of pull and the force of Gx. Should have made going to the left the positive direction. So we'll do that for now, but not a big deal. So let's see here. F pull is positive in this case, minus Fgx. This is the negative direction, going to the right, all over the mass. Multiply both sides by m, so ma equals F sub p minus Fgx. He's being pulled at a speed of 2 meters per second, which means that acceleration is 0. Let's add Fgx to both sides. And we're left with the pulling force is equal to F sub gx. Fgx is opposite the angle. So when we solve for Fgx in terms of Fg, it'll be Fg sine of theta, because it's opposite the angle. So the pulling force is equal to Fg sine of theta. We know Logan's mass. We don't know his weight, F sub g. So let's break down F sub g into mg. And that leaves us with the pulling force is equal to mg sine of theta. Okay, now we can answer the question letter A. How much work is required to pull Logan 60 meters along the 30-degree slope? Work, as we recall, is force times distance. In this case, we're looking at Logan's force. That's the pulling force, because that's what's doing work, and the distance along the x-axis, which is along the incline, which is 60 meters. So that's how the distance that the force is being acted upon the object. So work is mg sine of theta. That's the force times the distance. And now we just plug and chug. 70 kilograms times 9.81 meters per second squared times the sine of 30 degrees times, 60 meters. The work to pull Logan up the incline is 20,601 joules. So that's the amount of work required to pull him up the frictionless incline. Letter B, how much potential energy does Logan have at the top of the slope? The potential energy that Logan has is based off of the height of the slope. So that's the gravitational potential energy. And we don't know how high the slope is. But we know the resultant is 60 meters. And the angle is 30 degrees. So we could find the height of the slope using right triangle trig. Let me try and zoom out so you can see part of the problem. So letter B, we want to find the potential energy, Pe sub g. That's mg times h. But again, we don't know what h is, so we have to solve for it. Pe sub g is m times g. H is going to be the resultant times the sine of theta. So I'm just going to write d sine of theta, where d is 60 meters. And now we could plug and chug. Pe sub g is 70 kilograms times g, 9.81 meters per second squared, times the height, 60 meters, times the sine of theta, so the sine of 30 degrees, and in this case we get the same answer. The gravitational potential energy is equal to 20,601 joules of energy. And again, that height, d, is related to how high Logan is above the ground, not the distance he was dragged up. Last part of letter C, what power must a motor have to perform this task? Let's ignore the in horsepower. We'll use the standard units, which are watts. We have multiple formulas for power. In this case, we know the force to pull Logan up the hill, that's mg sine of theta. We also know the velocity that Logan is being pulled up at, that's 2 meters per second. So to calculate power, we can do the force of pull times the velocity. So the power will be, the force of the pull again is mg sine of theta times the velocity, which is 2 meters per second. 70 kilograms times 9.81 meters per second squared times the sine of 30 degrees times the velocity, 2 meters per second, gives us a power of 687 watts. Last problem for the day, or for however long you're watching this. Number 7, a 3,500 Newton piano is lifted by 3 workers, Bella, Max, and Elisa, at a constant speed to an apartment 25 meters above the street using a pulley system fastened to the roof of the building. Each worker is able to deliver 165 watts of power, and the pulley system is 75% efficient. So that 25% of the mechanical energy is lost due to friction in the pulley. Neglecting the mass of the pulley, find the time required to lift the piano from the street to the apartment. So let's write down our knowns. The piano weighs 3,500 newtons. That's the force of gravity. They're lifting it up a distance of 25 meters. The power that they exert, there's 3 people, Bella, Max, and Elisa, and they're each exerting 165 watts of power, which means the power they have, that they exert is 495 watts. However, only 75% of that power is actually being exerted on the pulley, so we have to do 495 watts times 0.75, because that's how efficient it is, which gives us 371 watts of power. And we want to find the time required to lift it. So if you look at our power formulas, we have power is equal to work over time, and power, or work, is equal to force times distance over time. They're lifting it at a constant velocity, which means that the force that they exert is the force due to gravity, or 3,500 newtons. Let's solve for the time. Multiply both sides by t, then divide by p. The time is the force times the distance over the power. Plug and chug, 3,500 newtons times 25 meters, all over 375 watts. Oops. And really, it's 371 watts. Not sure why I'm saying 375. Anywho, we plug and chug, and we get, it takes them 236 seconds to lift that piano up 25 meters. 236 seconds. That's it for this video. Thank you for watching. Hope you found it useful, and I'll see you next time. See ya.